So the first thing I wanted to talk about was why you have a dipole moment in water, right? So why is our oxygen negative and why is our hydrogen positive? I'm going to walk you through the entire process. And the goal of this, right, what you should be writing down on your piece of paper are things that you don't understand. You have this video, it exists, so don't worry about writing down every little thing that I say. What you should be writing are things that you don't understand, okay? You should say like, hey, I really don't understand why hydrogen is positive and oxygen is negative. You're going to write that down, and if you still don't get it, come up to me after class and ask me. I want you all to do well. I want you all to get the best grade possible. But part of that is, coming up to me, taking responsibility, and figuring out what you don't know. So hopefully this helps, right? So let's go ahead and talk about it. Now the end goal, right, is to show why oxygen has a negative charge and hydrogen has a positive charge. Why is that, right? Well, working backwards, the reason why oxygen has this negative charge is because all of the electrons are on oxygen, right? So all of the electrons are near oxygen and away from hydrogen. Now, why is that, right? So when we think about pull and what is pulling things, we know that electrons have a negative charge and protons have a positive charge. Yes?
Isn't there more like protons and oxygens than electrons are?
Exactly. So that's what we're getting to. That's perfect. So we'll go ahead and talk about that really quick. So with oxygen, we know that the atomic number for oxygen is 8, right? So atomic number meaning, what's the number on the periodic table? The number is 8 right here. So that means for oxygen, it has 8 protons, it has 8 electrons, and it has 8 neutrons. Cool. And then for hydrogen, because it has an atomic number of 1, it has 1 proton, 1 electron, and 1 neutron. Cool. So when you think about this water molecule right here, you need to draw out where all the protons are. So what we're going to do is draw out the protons. So what you'll notice is that if you draw out where all the protons are, you're going to have all of the protons for oxygen up top. And down here for hydrogen, you're going to have 1 proton on each side respectively. Okay, cool. Now you have to understand, 1 second. Go ahead, yeah.
Can you move it up?
Yeah, of course. Let me zoom in too. Alright, get this oriented. Alright, just focused a little bit. Is that better? Cool, thank you. Okay, cool. So when we think about our water molecule, we know that oxygen is going to have 8 protons, so that's what we drew, 8 pluses right there, and each hydrogen is going to have 1 plus on each side. So if you're an electron, you have to know that electrons basically float on the outside of the nucleus, right? So if you have, all of your protons and neutrons in the middle, right? N is for neutron, just in this case. So we'll draw, what it might look like for oxygen. So 4, 2, 4. Okay. So what you see right here would be like the nucleus. Of oxygen. And then on the outside of all of that, what are you going to have floating around everywhere?
Electrons.
That's right. I'll take a hand, but yeah, you're right. So you're going to have all these electrons everywhere, right? And they're just floating around. They're not committed to any particular space. they're in an electron cloud, right? And we're going to have 8 of those. And they all have the same behavior. 4, 4. Okay, cool. So you have these electrons that are able to float around, and what they do when they come up to this water molecule is they have to decide where they're going to spend most of their time, right? So they have the option of moving anywhere that they want in here, but they have to stay within inside this resonance, okay? So an electron has a choice. Am I going to go spend time right here near one hydrogen where there's only one proton, or am I going to go where there's 8 positive charges? So you have to think, right, where are electrons going to be more likely to go? And the fact of the matter is they're going to be wanting to go where there's more of a positive charge. And that positive charge pulling it is going to be on the, where is their greater positive pull? The oxygen or the hydrogen? The oxygen. So because there's more positives up there, all of the electrons are going to want to go in this direction. So now you have all these electrons that want to hang out by these positive charges. And because of that, you have all the electrons up here, and you have none down here. So what does that mean? For our water molecule, that means, effectively, that we're going to have a negative charge on the oxygen and a positive charge on the hydrogen. The negative charge right here represents an abundance and presence of electrons, whereas down here for the hydrogens, it represents an absence. There's no electrons down there. So that's basically what's going on with water. Yes?
Do they get drawn away from where there's less? Or did...
Yeah, it's kind of like this, right? All the electrons want to go towards the oxygen, and because of that, there's no more electrons to hang out by the hydrogens. So, yeah, let me try to think of an analogy, right? Let's say you were trying to decide where you wanted to hang out for lunch. That's a bad analogy. Basically, all the electrons are out on the oxygen, right? And there's no electrons to go by the hydrogens. So because of that, if a hydrogen doesn't have any electrons near it, all you're going to have is a positive charge because there's protons right there. Because remember, we started out right here with the positives. Those are still staying there. They're not moving. The positives are always going to be there. But because now there's positives right here, these protons, and there's no electrons near them, all you have are these lone positive charges right there. Does that help a little bit? Okay, cool. Yeah. So now you basically have a molecule that has a negative charge on one side and a positive charge on the other side. So how does this affect the macroscopic properties of water? What do we see in the real world? Well, one of the coolest things about water that allows us to, be able to live is the fact that it's going to be less dense as a solid than it is as a liquid. So we'll go ahead and talk about those properties of water right now. So the first one is going to be that it is less dense as a solid. Thank you. Let's do this. Less dense as a solid than as a liquid. So if you use something that's less dense as a solid than it is a liquid, what does that mean in terms of like floating? What's going to be on top? What's going to be on bottom? Yeah, the solid would go on top. So what you'll see in the real world, right, is you'll see an iceberg. So we'll just draw like a giant ice cube to simplify it. We'll call this our iceberg. And right now, it's in water, right? So right here we have solid water. And down here we have liquid water. And right now this iceberg is floating. Cool. Alright, so why does that happen? So we're going to draw two different images, right? One showing solid water and one showing liquid water. So we're going to go ahead and start out with the liquid water first. So when you have liquid water, basically all of the water molecules are disorganized, right? and they're all tightly compacted. So you're going to have, a water molecule, and this is for liquid water. And it's associating very closely with all of these other water molecules. But what you recognize, right, is that there's no real ordering here. They're all disorganized, they're all everywhere, and it's just kind of chaotic. There's no ordering. They're just mashed all together. And they're just freely associating between hydrogens and oxygens. And you can see right here that the dotted line represents the association between a negatively charged part of water and a positively charged part of water. Okay, so right here, the negative side of water wants to interact with the positive side of that hydrogen. So we keep on drawing our charges. We know that negatives are attracted to positives and vice versa. And we use that dotted line to represent that. Now really quickly, what is the difference between a dotted line and a solid line as far as this is concerned? Yes?
Dotted line means hydrogen.
Yeah.
Yeah, and there's a solid line is actually part of the molecule. Once again.
Exactly. So the way we would describe that, right? Just really quick, just to go over that, because that's kind of a hard thing. What is a dotted line? What's a solid line? So the solid line right here represents a covalent bond. Dotted line? Covalent bond, right? And this is the sharing of electrons. And this is literal bonding, right? So that's bonding, right? That's like concrete, that's solid. Now the difference, right, is if we have this dotted line right here, this right here is a hydrogen bond. And what this illustrates is an association. But it's not bonded. All right, sweet. So with a hydrogen bond, right, all of these water molecules are attracted to each other, but they're able to move around freely within each other. Now the difference is with a covalent bond, because the hydrogen and oxygen, and then the oxygen and hydrogen within a water molecule are covalently bonded, they're not able to break apart and then start running around everywhere. They're always going to be one piece. So what you could think about, right, is like your arms. We know, like, we can kind of like show our body as like a water molecule. Our hands being the hydrogens in our head being the oxygen, right? Right here, your arms, they represent a covalent bond, right? And the way you would kind of like show what's being attached to something, whether it's like a glass surface or, like when I get acid in my eye, we'll go over that, is just by showing that we're getting near those things, but it's not like we're getting bonded to them. So the whole point is, right, with the covalent bond, things are bonded, they're not being separated, but with the hydrogen bond, there's an association, but it's not a bond. This can still move around freely. Okay, so when we talk about solid water, with solid water, things kind of slow down a little bit. And what you'll notice is basically things want to be as stable as possible because they're in that space for a long time. So basically what happens, right, is you get this beautiful ordering of water molecules lining up because now they're becoming crystals. Okay, cool. All right, so you have something like this forming. And right here, what you'll see is there's still an association between the oxygens and the hydrogens. But now you have this space in between where all the ordering is happening, right? So you have space in between right here, and right here, and right here. And if you're comparing that to liquid water is all jammed up within itself, right? It's all very crowded. So because of that, you have smaller spaces. They're not as large, and it's more compact. Now, the reason that this relates to density, right, is if you're more packed together, and we'll kind of define density, right? With density, you're going to be more compact. Meaning that you're going to have more mass within a volume. Than something less dense that is going to have less mass within that volume. Cool. So we know that if you had, if you had a space and it was the same space, you'd be able to fit more water molecules in liquid water than you would for solid water. Okay, so let's say, we had like a box, right? And the box was, I don't know, like 1 foot by 1 foot by 1 foot. Okay, so we have this box, right? Just trying to, let's see if you understand. So it's 1 foot, right? 1 foot. And we're almost done with this. Cool. And over here we have the same box. So when we think about density, if you filled up both boxes with the same amount of water, but one was with liquid water and one was with solid water, which box would you expect to have more water molecules in it? And I'll take a hand. So if you had solid water, and then you had liquid water, and they're the same size, so which box would have more, the liquid water or the solid water? It's more dense, right? And we know that because these are less ordered, they're all clumped together. Less ordered, more crowded. And down here, they're more ordered. Less crowded. Okay, so you can fit more water molecules Okay, cool. All right, so that kind of talks about density. And we'll take a break halfway through. We got 15 more minutes until a break, so, looking out. So right here we can see that because of hydrogen bonding, when you have hydrogen bonding between a solid and a liquid composition of water, right here the bonding is going to allow us to form this more ordered structure because now they're able to line up in this beautiful shape. And because it's solid, right, it's going to want to form a crystal. So this crystal shape is going to be established, and that's just the way it goes. Because there's more space within the spaces of that crystal than in the spaces of liquid water, this is going to have more space within it, so it's going to be less dense. And because it's less dense, the solid water is going to want to float. With the liquid water, now you're going to have less space, or you're going to have less space in here, so it's going to be more crowded, and because of that, more water molecules are going to want to fit inside that box in the same shape, so it's going to be more dense, and it's going to sink, whereas the ice is going to float. Okay, so that's what's going on there. The thing that I would expect you to know for your test is I'd want you to be able to tell me that liquid water is going to be more dense than solid water, and I might give you a shape, and you're going to have to tell me which one is solid water and which one's liquid water, and because of what effect, and that would be hydrogen bonding. Okay, so that's what's going on there.
The solid water still has hydrogen bonding.
Exactly, it does. So the reason why you have this ordering is because of the hydrogen bonding. So that's why you have an association, and they're linking up perfectly. It's because, go ahead.
How is the bonding different than the liquid?
So the same bonding is happening, but in the liquid shape, you're moving around more freely, and now you're more like clumped together, right? Whereas with solid water, you have time, and you're forming a crystal, so now there's space in there. An analogy you could think of, and it just ran into my head, right? Is think about this, right? Let's say you're going to a concert, right? And they let everybody in at the same time, and now you're just running in, right? Everybody's going to get really crowded once you hit the go point, right? Where there's like a little, not a go point, but maybe like the front of the concert venue. Everybody's going to be crowded, you just got there, right? But if you give it time, if you started to wait a little bit, and you wait like an hour, everybody's going to start to realize, okay, I kind of want my personal space. And everybody's going to have a little bit more of a bubble around them. So right here, you have to wait until you're solid water. You have to freeze, and now you have space in between, right? Time has passed, now you have space there. Liquid water is going to be a little bit different. Liquid water is just like you ran into the concert, you just got to the front, and now everybody's crowded. We spent a lot of time on this. Let's keep on going. So right here, this is density. Okay. Also, I'm going to be posting all these notes online, so there'll be a PDF available. Cool. All right, so the next thing we're going to talk about, the next effect of water is the universal solvent. So if I have acid in my eye, right? So right here, someone was messing around in the lab. We were doing that little I exercise and I blow into a tube, right? Somebody got it in their eye. What do we do? So we just got acid inside of our eye. Now let's say you're at home, right? Let's say you're at home and you're messing around with your laundry detergent. And you're messing around and you get laundry detergent in your eye. So we're going to have these two different scenarios. Okay, so now we have base inside of our eyes. How does water remove this from our eyes? So, they always say, whenever you get acid in your eyes, or you get base in your eyes, or you get any kind of chemical to wash out your eyes. That's what we have, that eye wash station right there. But how does that work? So basically what's happening is you have this stuff all inside your eyes, and what's going to happen is these right here are going to be carried out, right? Water is going to come into your eyes. So we're going to go ahead and have water, right? So we have water. We introduce water into our eyes, and the thing that's going to happen is we have our H+, and then all these water molecules are going to surround the hydrogen plus ion, and they're going to carry it away. So now you have this H+, which is the acid, and these oxygens, which are negative, are wanting to attract with this positive hydrogen. So you have a negative charge, right? Thank you. Cool. All right, sweet. So we're talking about right now getting acid inside your eye, right? So we just got acid inside of our eye. This is H+. We just got base inside of our eye. That's OH. And what I'm trying to show you is that water is a universal solvent. So how does water break up all of these things inside of our body. Why is it such a great way to clean things? So when you have H plus right here, this H plus, which is acid, has a positive charge. When you introduce water into this equation, right, into this situation, the oxygens from the water molecule are going to be attracted to the positive charge of the acid, and it's going to carry it away, right? So final step, carries, washes acid away. Now the same situation is going to happen for OH, except in reverse. So now, what you have is you have water being introduced, and now you have OH right here. And now, instead of the O wanting to interact with this positive charge, now we have a negative charge. So what do you think is going to interact with this negative charge?
The hydrogen.
The hydrogen, because it has a positive charge. Excellent. So right here we have hydrogens. Wanting to interact with this negative oxygen, or the negative base, right? And in the same way, it's being carried away.
Oh my god.
Okay, let's chill out. Cool. Alright, so that's what's going on right here. And what this is depicting is that water is a universal solvent. So we've gone over density, now we're going over universal solvent. The next things that we're going to talk about, yes?
What is OH base?
So yeah, that's a great question. So what is a base, what is an acid, right? A base is quite literally an H+. So if you look over there at the periodic table, you notice you have a hydrogen, right? So what happens, right, is once that electron is given up, if you have something that has a positive and it has a negative, right? So a positive and a negative, and this is in an H, a hydrogen, right? Right here it's neutral, and that's what you see inside the periodic table. But what happens, right, is that electron is usually given up. So now you give up an electron, and all you have is this positive charge left. So what happens a lot with hydrogens that are just floating around is they'll give up their electrons so they can be happy, and what they'll be is just a floating proton. And that floating proton is positive. Now what's dangerous about that proton, why acid is so dangerous when it hits us, is there's all these things inside of our body that have charges in them. So when you have this very small thing that's positive, it can get anywhere and it can react with anything. So the reason why acid is dangerous is because it can get in anywhere and it can react with everything. So when you have that on a large scale, it's kind of just like sending this crazy kamikaze thing that can just like get anywhere, react with anything, and change any environment. So that's very dangerous in your body because a lot of the time you want to keep these processes that are inside maintained, right? Everything is happening for a purpose, but when you introduce hydrogen, it can just mess everything up. So it's really interesting. And the same goes for OH, where it's negative. So here's a little fun side story. This has everything to do with biology. Now the big craze that happened about like maybe 5 years ago was antioxidants, right? Do you guys know what antioxidants actually do?
I've heard it before.
Right, so right here, we've heard about it, right? So you have antioxidants. Why are antioxidants such a craze? So you have these things inside of your body that run around and they have, they have their charges. That's fine. But let's say if you smoke like cigarettes, right? They're terrible. Now the reason why cigarettes are terrible for you is you're introducing all these things into your body that have these really nasty charges, and they're going to interact with everything. It's kind of like acid or base. They're just going to interrupt the processes and bind to things inside of your body. Now what antioxidants do is they go inside your body and they actually neutralize the charges of items like that, like, you know, the carcinogens, the things that you would get from like a cigarette. They neutralize them so they can no longer interact and destroy things that are happening inside of your body. So let's say, right, and this is a tangent, this won't be on your test, but it is kind of helpful information for life. Let's say, you know, you pass somebody who's smoking a cigarette and you breathe in some of the smoke. Well, you have all of these bad things inside. So, you know, you have bad carcinogens. And inside that carcinogen, it has all of these nasty charges, right, that are inside of it, that are going to interact and disrupt regular processes in your body. Now, this is the kicker, right? Why are antioxidants such a big thing? So, what charge does oxygen have? It has a negative charge, that's right. So, what antioxidants do is they're quite literally, right, they neutralize things that have nasty charges, like an oxygen. So what they're going to do, antioxidants, they're going to come in, and for all the positive charges, they're going to have a negative charge, right, that can go ahead and neutralize. And for negative charges right here, they're going to have positive charges that can neutralize. So the reason why antioxidants are so helpful for our body is because we're able to neutralize charges that would be harmful otherwise. So able to neutralize getting a detention. Let's see. So we got 3, right? So, cool. If I see anything, it's going to be a detention. You all have your warning. Cool. Let's keep on moving on. So right here we went over universal solvent, and we talked about antioxidants. We're going to go ahead and go on to the next property of water. Yeah, that's fine. This will take a little bit of time. We only have 2 more effects to talk about, so we're almost done with water, and then we'll talk about our macromolecules, which will go by pretty quickly. That's pretty much just categorization. It'll be straightforward. Okay, so these are all going to be on the website, so don't worry about that. I'm going to go ahead and take it away. All right. So the next thing we're going to talk about is cohesion and adhesion. Okay, so cohesion. And we have adhesion. Cohesion is going to be attractive forces between the same type of molecule. Adhesion is going to be attractive forces between different types of molecules. So same, different, right? Same, different. Okay, cool. So the classic example we know for cohesion is when we have a penny, right? We have a penny, and we've been adding all of these water droplets on top. So adding water droplets. And what you notice in this water droplet that's building up is it's larger than the penny. You have this weird distension right here. So why is water able to distend over the boundary of the penny? Well, I'll tell you why. So the reason why it's able to hang off the side of the penny is because on the side right here, you have these crazy things that are hanging onto each other. They're basically preventing, the edges of the water molecule from falling off. So I'll go ahead and draw a picture of that. So right here we have the edge of a penny, right? And now you have this giant distension that's hanging off. So why doesn't this water molecule on the end want to fall off? Why is this guy right here over the edge of the penny but not falling off? What is going on there? So what's happening? Oh, yes.
It's the hydrogen bonds.
Exactly. It's the hydrogen bonds of all the other water molecules that are over here that are keeping this guy from falling off. That's great. Good job.
It's teamwork.
Yes, teamwork. So we have these oxygens, right? And they're holding on to this guy that's trying to escape. And they're saying no. We're holding you back. We're all working together to keep this guy from falling off. So you have all of these right here holding on to the positive charge of this hydrogen with their negative charge on the oxygen. Yes?
Is this like when you give us that example?
Yeah, and I will bring that up, right? And they're all trying to prevent this guy from escaping. Trying to escape. But can't because water molecules are holding it back through hydrogen bonding. So here's a little bit of a story for you, right? So probably the second week into me being here, I was feeling kind of nostalgic, and I was like, man, I'm going to look through the yearbook. So I looked through my senior yearbook, and I had this page of senior quotes. And one of my good friends, his name was Connor Israelian, who's our ASB president, he had this quote where his favorite memory was trying to jump into a trash can. Yeah, I'm going to repeat it again.
Oh, yeah.
Oh, that's a good story. So this guy, he's trying to jump into a trash can, right? But what I want you to do, hey, let's keep it together. So this guy is trying to jump into a trash can. See, that's how good of a story it is. You guys remember it. All right. So you have this guy, and he's trying to jump into a trash can. Off the edge of an amphitheater. But who is holding him back? If you guys remember the story so well, let's have some interaction.
The
The administrators, that's right. So these administrators, right?
That have super long arms.
That's right. So these administrators. Hey, seriously, the noise has got to die down. Okay. Cool. So you have these administrators, and they're all working together to keep this gentleman who's trying to jump into the trash can from jumping into the trash can. And the more people you add on to this chain, the less likely it is for him to jump into the trash can. So, more people in chain, greater strength in holding him back. escape, right? So now you have this juxtaposition between this water molecule that's trying to escape and, my friend who is trying to jump into this trash can. So right here you have all these administrators trying to hold this guy back, and right here you have all these water molecules trying to hold back this water molecule that's trying to escape. So right here, the reason why we're able to have a distension of this bubble, or of this water molecule on top of this penny, is because the stuff that's on the edge is being held back by all the other water molecules through what force?
Hydrogen bonding.
Yes. All right. Sweet. Excellent. So we're going to go ahead and talk about adhesion, right? Really quickly, it'll be very short. So the reason why you have water that pools up on a window, right? So you have a window, and we'll go ahead and zoom in. And this window has silica in it, and it has oxygen. That's the structure of glass. So we're going to go ahead and draw in this box. We'll keep it consolidated within this box for adhesion. You're going to go ahead and have the surface of water, right? I mean not the surface of water, the structure of glass. So it's going to have negative oxygens on the outside, and then on the inside, you're going to have silica. Now, I do not expect you to remember the shape of this. On the exam, I would give you a shape like this, okay? So now you have these oxygens right here, and this hydrogen, basically you have this water molecule that's hanging on the edge of the surface of this window, right? So this is the surface of a window, a glass window, and right here you have a water droplet that is stuck to the window. So, what's going on with that water droplet, right? You have these oxygens right here, and then what's going to be happening is what's going to be interacting with it. Yes, they're very good. Okay, so we have these hydrogens right here, and they're wanting to interact with the oxygens inside of the glass. So when it starts to rain in Fresno, and you're driving, and your parents are like, man, I hate this rain. Why is it beating up on my window? I got to use my windshield wipers. You can tell them with complete certainty why, at an atomic level, water is beating up on your window. That's pretty powerful information.
You can just be like, yo, it's raining. I mean, it's supposed to hit your window. And it's gonna stay on because your window's got like magic.
Cool. So we can see water right here, and it's interacting with the oxygens inside the glass. The oxygens are going to have a negative charge, and our hydrogens are going to have this positive charge. And the force that's holding them together through attraction is a hydrogen bond. So we see this trend of water molecules trying to escape, but they can't because of the attraction between something negative and something positive inside the water molecule. In the case of the window, it's this negative oxygen interacting with the positive hydrogen of a water molecule. In the case of our water droplet, what's going on here is our water droplet is trying to escape, but it can't because all the other water molecules are holding it back. So negative and positive charge interactions through hydrogen bonding. Cool. All right, so let's go ahead and move on to the next part, which is heat capacity. And this is just the same piece of the same tail, right? So right here we have heat capacity. Oh, thank you. Just zoom out a little bit. Cool. So heat capacity. Heat capacity is very straightforward. Step one, right? We're going to have a pot of water, and there's a heat applied to it. Heat applied to pot of water. Now what's happening to this pot of water is now all of these water molecules are getting heated up, right? And the hydrogen bonds between them are basically, there's a lot of energy being put into them, and now they want to break apart. Now what happens when you start to heat up water and the water molecules try to escape, right? What do we call that event? We call it boiling, right? And what do we call water when it turns from a liquid to a gas? We call that
Photosynthesis.
Vaporization.
Evaporation.
evaporation. That's right.
Oh, that's right.
Hey, let's bring it back. Okay. So, right here, right, we have our pot of water. And one of our water molecules is trying to escape. It's received water molecule has received enough heat energy to overcome being a liquid. Wants to evaporate to become a gas. Okay, cool. So that's what's going on right there. Now what you recognize, right, is you have this water molecule and it's trying to escape. It's outside of the water. But why is it not able to escape? What's going on? They're holding on to that water molecule. See, it's the same story. So, when we think right here, right, we go right here, and we see that this water molecule is trying to escape. Water trying to escape. So what happens? You have all these water molecules below that are hanging on to each other because they're still in the liquid form, right? But they're also going to be holding on to this water molecule that's trying to escape. So right here, right, we see the negative charge of oxygen, and we see the positive charge of hydrogen. And, we write out all of our charges. And we can see the interactions between the positives and the negatives. Okay? And because of that, this guy's trying to escape, but it can't because there's these bonds that are holding it back, right? These hydrogen bonds. So hydrogen bonds prevent evaporating water from escaping. So what does this mean about heat capacity? Why does it take a lot of heat in order to evaporate water? Well, the reason why is you have to overcome this event right here, this phenomena where the water's trying to escape, and now you have this extra force that's keeping it from escaping, right? So how do you overcome that? You have to add even more heat. So we have to must add even more heat must add even more heat energy to overcome hydrogen bonds between water molecules. And because of that, because of this crazy hydrogen bonding phenomena, and you having to add a lot of heat in order to evaporate it, you can have a lot of heat inside of water without it evaporating. So now you have water, right? And you're trying to make it evaporate. But now you have to add an extraordinary amount of heat in order to get it to evaporate. So because of that, you have to put a lot of heat into it in order to get it to evaporate. So now you can have a lot of energy in there. You can have a lot of heat. You have the capacity to have a lot of heat within water. So you have the capacity to have a lot of heat within water. That's where heat capacity comes from. Okay, so water can hold a lot of heat before evaporating. So now you have this crazy thing right here, right? You have water, and we've talked about how it's less dense as a solid than it is a liquid. We talked about how it's a universal solvent. We talked about how it's able to attach to itself and other things through cohesion and adhesion respectively. And now we've talked about heat capacity. Water is incredible, and I hope that by the end of this, whether you're watching this at home or you're in the classroom right now, you can appreciate that through charge interactions, it's actually very cool. It's an amazing thing. And you guys have a lot of power inside your heads because of the information that you've just learned. So, yeah. Now we're going to finish off, and I'm feeling optimistic. We're going to have some time left over. We're going to go ahead and go through our macromolecules, okay? And what I'm going to do for that is I'm going to go through the study guide that I had assigned. And remember, the questions on here will be very similar to your final exam, so take advantage of that, okay? So we're going to go ahead and start off with this.
Is this the last thing?
Yes, today. Okay, cool. So we're going to talk about a virus, right? So with the virus, how are you on that? Good? All right, sweet. So the first thing we're going to do, right, is talk about a virus. So we went over this, right? A virus has a shell, and then it has these receptors that it tries to use to match up to an organism or another cell to release its genetic information inside. So let's go ahead and just, forgetting about the intricacies of a virus, go over its anatomy. What is this shell of a virus made out of? What macromolecule?
Protein.
It's made out of a protein, that's right. So we look right here. Okay. So what is this shell made out of?
Protein.
Got it. So the answer is going to be a protein, right? Now let's go ahead and go over this. What is the monomer of this macromolecule? So right here we have a protein, and this is the monomer, right? This is the macromolecule. Macromolecule class, right? Okay, so now we have the macromolecule. What is the polymer of a protein? What do we call that? No. We call it a polypeptide, right? Cool. All right, so now we have to think about the monomer. What do we call the monomer of a protein? And you can think back to protein synthesis, right? What does tRNA have on top of it that brings in, that allows us to build a protein? A tRNA is going to have what? What's it going to have on top? It's carrying one of these, right? So when you think right here, what is that guy? Yes.
Amino acid.
Amino acid, that's right. So when you think about the level of organization that's going on right here, you use monomers as single pieces, right? So these are single pieces that can be used to build and elongate. These single pieces of monomers are used to build polymers, which are multiple monomers. And when you think about the different types of chains, we call these different types of macromolecules within the protein class. So various types. of chains. Okay, cool. Let's go ahead. There are 20 different monomers of this type of molecule. Okay, so we're going to go ahead and talk about the shape of this, right? So what does the shape look like? Right here, the shape of an amino acid is going to look like this. Cool. All right. So who can tell me what this R means down here? Oh, we got to move up. What is up with that R? You got this. No, it's not a ribosome.
Does it start with R?
No. So I'll just tell you, right? So I let you know, right? So what's kind of cool about this is if we look at our amino acid chart.
That's cheating.
No, it's
Yeah,
not.
or, but it
So right here, these are all the different types of amino acids that we can get, right? Check it out. We have proline, right? We have isoleucine, whatever. There's all these different types. But they all have the same basic shape, which is this. This is an amino acid. So how do they differ? They basically differ by the R group that's right here. So this R represents any type of amino acid that it can be. But all amino acids have this basic shape. So they have this basic shape. But the way in which they're unique is this right here. So the 20 different types. The 20 different types of amino acids have different R groups. Okay, and that's pretty cool, right? So an analogy we can make to that, right, is we could think about our Lego man, right? So if we go ahead and draw our Lego man, we know that all Lego people have the same basic body, right? So we're going to go ahead and draw a Lego guy.
Heck yeah.
Whatever. But how do you change one Lego guy from like a fireman to like Batman, right? You change the head, that's right. So we have all of these different types of heads that we can put on top, right? So we can make it like, I don't know, like a baseball guy. We can make this guy. I have no idea, right? I can't really draw that well. We can make this guy like, I don't know, he's going to be an astronaut, so he's going to have a giant like mask on him. Okay? So what you can do is you can switch out Lego heads on this basic Lego body. And what I mean by basic is this is what every Lego has, right? So in the same way, every Lego person has this body, every amino acid has this basic shape, okay? And the way that you make amino acids different from each other is you have this repeating subgroup down, you have this R group right here, okay, which can be substituted out of things. And right here you have the heads that you can switch out with other types of things. Cool. All right, so we've gone over that. This right here is how you have unique and different amino acids. Okay, cool. Now, what do you call the joining and separating of amino acids? We call the joining what? joining is referred to as a condensation reaction. And the separating is referred to as what? That's right, hydrolysis. Okay, so now we've gone over proteins. Yes. Yeah. If you want to stand up, you totally can. Okay, so the joining and separating amino acids. There you go. Yeah, I understand. It's very long. Cool. All right, so we're going to go ahead and go over the next part right here, which is going to be what do we call the membrane of a host cell, right? So we have our host cell, and right here the membrane is made out of what macromolecule? It's made out of, I'll take a hand. It's made out of lipids, that's right. So, what is this membrane made of? It's made of lipids. Cool. All right. So this is our macromolecule. And also our polymer, right? Now right here, what is the monomer of a lipid? I'll take a hand. What do we call that thing? It's a fatty acid. Okay, all right. If you want, just in the back, right? Just find the corner. There you go. I'll let you do that. All right, sweet. All right, but good job. That was really good. Cool. All right, so what we're going to do right now is I'm going to go ahead and draw out some of the shapes. What are the three different types of lipid classes? There's three. So right here, we have a couple different types, right? So what are the three polymer types? Okay, so the three polymer types are going to include triglycerides. They're going to include steroids. And they're going to include phospholipids. Thank you. Okay. Yeah, don't come this way. Yeah. Go the other way. All right, thank you. Okay, so we've got our triglyceride, right? And what do we have for our triglyceride? Okay, we're almost done, right? Just keep on going. We're almost done. Okay, so our steroid, we'll start with the triglyceride. That triglyceride is going to have a couple different things going on. So it's going to have, and these are all carbons, right? It's going to have what's called a glycerol group. And then coming out of it, it's going to have these repeating subunits called fatty acids, right? So for one of these, it's going to go ahead and look like this. So we have these. So what you can see, right, is you have these different things going on. You have a glycerol, and then inside of every triglyceride, you have this monomer. What is the monomer of a lipid? We call it a
Fatty acid.
fatty acid. That's right. So right here you have 3 fatty acids. And what is the point of triglycerides? Triglycerides are great at energy storage. So that is their purpose. So right here, we're going to go ahead and put it right here. Energy storage. Okay, now steroids.
I take steroids.
Yes. All right, so steroids. All right, so steroids right here. If we're concerned about our body, right, and we don't do this, right, steroids basically, you know, the way we know them in common culture is that they get us large. Muscle-wise, they give us, like, you know, abilities beyond our normal capacity. So the reason why steroids are able to do this, the reason why steroids are able to do this is because they're great at signaling and communicating with our body, telling us, you know, to put out more muscle, to put out more of whatever that steroid is aiming to do. So right here, our steroid is for communication in the metabolism of our body. Okay? Now, the steroid shape is a little bit complicated, so I'm just kind of going to draw it. This one I'm not as concerned with. It's a little bit complicated. So basically you have all of these rings. And can anybody tell me what these rings are made out of? Whenever I draw these like shapes, what is each corner? What is that representing? No. It's representing what element?
I don't know.
Does it start with P?
No.
Does it end with a lip?
Does it start with the letter?
Yes. Starts with the letter.
Oh, what's the letter?
All of these are carbons.
Carbons.
Yeah. No.
Oh my god.
I'll give you a listen to you.
I'm so.
Hey, let's bring it down. Okay, cool. So right here, we have our steroid, and we know that our steroid is really great at communication in the metabolism of our body. So that can include a lot of things, whether it's, you know, somebody trying to get an advantage on a race, so, you know, their body is reinforcing the idea of more muscles, or it can be like maybe you're sick, right? And you need to increase the abilities of your immune system. You can take steroids that allow you to do that. Steroids are in many cases a medical therapy. Okay, cool. So phospholipids, right here, we're going to go ahead and draw the shape. Now right here, what are phospholipids used for? They have a really specific use, and they're incredible. What are they used for? Every cell uses phospholipids. Those phospholipids are in what part of the cell? I'll give you a clue. Right here.
I can't see that.
Oh, right here, phospholipids are used to build these. They build, nope. Right here, read this sentence.
What is this membrane?
I said they make the membrane.
They make the membrane.
Oh.
They make the membrane of the cell. The membrane is the wall on the outside of the cell. Phospholipids, right? They're great at producing, providing support through membrane of the cell. Providing support through membrane of the cell. Okay, cool. So a phospholipid is basically going to look like this, right? It has 2 fatty acids that are coming off of it. Do that. Redo this. So we have this is a carbon, and then we have this right here. And then we're going to go ahead and have this right here. We're going to have a phosphate group. And then at the top, we're going to have a nitrogenous. So, I don't expect you to know every part of this structure, but up here, you have an amine group. Right here, we have a phosphate. And down here, you have 2 fatty acids. Okay? So, there's something that's really special. There's a connection right here, right? So, let's not forget about that. Okay, so there's something that's really special about fatty acids. Now, the reason why lipid membranes are able to move around and be very fluid is because they're not able to stick together. So, what you could think about, right, is why are these not able to stick together? One of these has a kink inside of it. What do we call that kink? We call that bond, it's either saturated or unsaturated, right. So, right here, I want you to go ahead and tell me, right, which one of these is saturated or unsaturated? This one right here or this one right here? Yes.
Top one is saturated.
Very good, that's right. The top one is saturated.
But I guess
Okay, alright. So the top right here is saturated. And you know that it's saturated because it has no double bonds. No double bonds. Okay. And down here we know that it's unsaturated because it has a double bond. Okay. A or multiple double bonds. Okay. All right, sweet. That right there is our lipids, right? So we got lipids.
Wait.
Okay, we got to keep on moving. All right, sweet. So right here, A. Shh. Cool. We have genetic information inside of our cell. What do we call this genetic information? We call this DNA. That's right. So DNA, we can call it RNA, right? And this is our virus. So our virus is basically trying to deliver its DNA or RNA to another cell. So what is the macromolecule class of DNA or RNA? We call it a nucleic acid. So the macromolecule
Heck yeah, bro.
is called nucleic acid. Right here, the polymer is going to include DNA or RNA. Right here, what is the monomer? What is the monomer of DNA or RNA? And I'll take a hand. What do we call the monomer of a DNA or RNA? They're made of a whole bunch of
RNA.
That's the macromolecule class. What is the monomer of a DNA? We call it a nucleotide.
That's what I said. Oh.
I said that in my head.
Hey, let's keep it down. Okay, what is at least one example of nucleotide molecular structure? So we know that for a nucleotide, the thing that we need is we need a phosphate, we need a, let's go ahead and draw it out, we need a deoxyribose, so we need a sugar, and then we need a nitrogenous base. Now what are examples of these nitrogenous bases? It's the way that all these different nucleotides are different from each other. So these different nucleotides can have letters like A, T, C, G, right? So these nitrogenous bases can take on and are different through these different subunits, right? An A, a T, a C, or a G, or in the case of RNA, it's going to have a U. So that is the basic shape right here of a nucleotide. It's going to have a sugar, it's going to have a phosphate, and it's also going to have these nitrogenous bases right here. Okay, cool. What is the purpose of this macromolecule right here? The purpose is to hold all genetic information for making proteins. Cool. So that's the purpose of our nucleic acids. Cool. Let's go ahead and finish off with our last one right here. So our last macromolecule class right here is for signaling, structure, and energy. Alright, so sweet. What is the name of this macromolecule right here that's for signaling, structure, and energy? We call it a carbohydrate.
Carbohydrate.
And this right here is our macromolecule. Okay, now the polymer can take on names like starch, right?
Starch.
Or polysaccharide. And the monomer of these is going to be called a monosaccharide. Okay, now let's go ahead and talk about it, right? What is the molecular shape of a carbohydrate? So, molecular shape of a carbohydrate. We're going to have a long chain, right? And one is going to look like this, right? So we have this ring type structure. And basically, this is going to be one carbohydrate, one polysaccharide. And, you know, the way that they differ is they have different things coming off of them. They can have different groups coming off of this side of the ring and whatnot. So that's how they vary. This ring structure is very basic. This is what all of them have, but the different additions on them is how they differ as different types of monosaccharides. So you can have glucose, you can have fructose, right? Glucose, fructose. And remember, all of these are used for energy. So when we think about cellular respiration, right, we know that glucose can go into cellular respiration, go through glycolysis, the Krebs cycle, and the electron transport chain to produce ATP. So right here, we have one, right? And when we add on another one, we can call it a disaccharide. And then you add a whole bunch of them together to go ahead and make a polymer like a starch or a polysaccharide. Okay? Okay. So right here we've gone over the purpose of a carbohydrate. We've talked about what it is. We've talked about the polymers. We've talked about the monomers. And here I provided you a shape. Okay, cool. That is everything that I have planned out for the macromolecule.